All right, guys. Just kind of talk a little bit about the course and how we're going to approach things. And then we'll get into the start of some new information. The homework is still being through website, so everything grade-wise, grading-wise is going to be consistent with what we've been doing. And I don't believe there's anybody, last class we had 2 people that were new to Trig, so nobody here new, right? Okay. Well, he was in first period. All right, so what's going to happen is, because of our college algebra background, we're going to continue to do some of that stuff with like transformations of functions and all that kind of stuff. That will overlay into this course a little bit. The first 2 chapters are going to be dealing with your trig functions, sine, cosine, and tangent, and then their reciprocal functions, secant, cosecant, cotangent, by the understanding of right triangles. Okay. The next chapter, chapter 6, will then be the same exact stuff, but through the use of what we call the unit circle. Okay, which is important for us to understand that when we use the unit circle, ultimately, because of the way the unit circle is built, we're still using triangles. Okay, and we'll talk about that as we get there. But that's a lot of review. You look up here, you see under chapter 5, you've got trigonometry of right triangles. So that's going to give you a missing side. I'll give you an angle measurement, give you a side length, and ask you, find the variable using sine, cosine, tangent, and that kind of stuff. We keep going through that stuff. We start talking about our sine inverse, our cosine inverse, tangent inverse in section 5.4, which is now I give you side lengths, and I ask you to find an angle measurement. Okay, and then you see 5.5 and 5.6. Those are law of sines and law of cosines. Those are things that we've already done, right? So this chapter is something, this should be old information. Okay, now that being said, when we start talking about sine, cosine, and tangent and start analyzing that stuff, we'll talk a little bit more about what our calculator is doing when I type in sine of 30 and it spits back 1/2. Why does it know to spit that back? Okay, that's kind of the investigation that I think is important for us to understand at this level of trig. Okay, because you have a good kind of base foundation of trig already. Okay, using what we've talked about in geometry. There at the top it says much of the early parts of trig will incorporate procedures that help you build skills for completing applicable problems later on. There might be times through the first couple of weeks you're like, what are we doing this for? Why am I just taking this number, multiplying it by 180 over pi, and getting this output? Why am I doing it? Okay, it will make more sense later on. Okay, trying to build individual skills that then later on we can put together and mesh together to really address a real life phenomenon. Okay, and we'll see the application of those skills later. This is one of the number 1 issues that calc students struggle with, is the trigonometric portion of calculus. Okay, finding derivatives, finding integrals, those things all have procedures attached to them, and they're pretty easy with polynomials, but the procedures get more difficult when you start talking about sine, cosine, and tangent inside your equations. If you have an understanding of how to deal with sine, cosine, and tangent in this course, it makes the transition into calculus so much simpler. Okay, but when you get to calculus and you need to talk about sine, cosine, and tangent and all the things that are going on with it, if you don't have a solid trig background, you're going to be learning trigonometry and calculus at the same time. Does that make sense? Trying to reteach yourself that stuff, and that's going to then take away or distract you from the actual calculus. So a lot of the first 2 or 3 chapters, like I said, information that we have discussed and learned in previous courses. We will take different kind of perspectives of it, different viewpoints, talk about it a little bit more in depth. It says a lot of trig is used to explain physical phenomena. Okay, you're going to see things that you've talked about in physics class. Okay, and it's probably going to frustrate you because once we talk about it in here, you're going to see the simplicity of it, and then say, oh, that's all I had to do in physics. That's seriously what it was. But it took me 4 hours to do that one problem, and you just showed us the idea now. It can take maybe 30 seconds. that's going to frustrate you. But then at the same time, hopefully it's a learning experience that, okay, now I understand the purpose of mathematics, and allows me to kind of navigate things, navigate other areas of science a lot easier. You guys talk about vectors in physics. We'll talk about vectors in here. There's a lot of things in a physics class when you're talking about angle measures. You talk about forces and all that kind of stuff, right? And how those forces impact each other and the directions that they occur. There's a lot of trig there. So that's something we'll talk about. There are things in trigonometry that we will do, especially with like complex numbers, a plus bi stuff. Okay, the multiplication of a plus bi is, if I take like 2 plus 3 and I ask you to square it, you can do that. If I ask you to cube it, you can do that. If I ask you to raise it to 24th power, you don't want to do that, right? Okay, you don't want to do that foiling. It'd be about 12, it'd probably be around 20 different foilings you'd have to do to get that. Trigonometry allows us to convert things into a different form. Okay, we start dealing with a different coordinate system we call polar coordinates. And allows algebraic processes to be conducted a lot quicker if our ordered pairs are in what we call polar form instead of what we call rectangular form, like x and y's. And we'll get to that later on, but that's just kind of a snapshot that trig a lot of times allows you to do things in other areas of math or science very quickly. Everything's going to be the same, so record class, all that kind of stuff. This chapter is all broken down in these sections. You click on these sections. Inside them, there's still going to be applets from GeoGebra that I've created. There's still going to be videos. It's where I'm still going to put the recorded videos for each class. So it's inside those. But what I will do, because I just like the way that I've got this set up right now, I'm going to, for the notes for all of Chapter 5, I've just kind of got them right there and kind of a continuous PDF that we'll roll through. We'll do a lot of examples. There's more examples in that PDF that I've made than there are throughout the PowerPoints of each of those sections. But those PowerPoints are still there, but they're going to say the same thing that the PDF does. WebAssign will be the same. Okay, no new login into that. It's just continuous for what we've been using. So, all right. The number one thing that I think is important for us to use is GeoGebra. It allows us to manipulate and visualize angles and what we're trying to do with those angles and represent with those angles than what maybe Desmos or your calculator, your TI-83 or 84 does, or just drawing things by hand. In a trig textbook, there's a lot of static pictures, and if we can move them around and see what they're really referring to, it makes things a lot easier. All right. So if you don't have GeoGebra, I do strongly suggest that you take a little bit of time to download that. I want to do a little bit of a explanation of something real quick, because we're going to, and we'll talk about this several times. But I want you guys to see why we have the measurements that we use. So, for instance, how many degrees are there in a circle? 360, right? Anybody know why? Essentially because a long time ago, somebody said that's what we should have. And that somebody was the group of people called the Babylonians. You guys have heard them before, right? Okay. So the Babylonians knew was that we've got a hexagon here, right? They knew we could create a hexagon through taking 3 equilateral triangles, okay? And they knew if we got 3 equilateral triangles, then we have 3 equal angular triangles, correct? Okay? And if those are equal angular triangles, what are all of those angles in those triangles positioned there at the origin? They're all what degree? 60 degrees, which is ironic in a way, because does anybody know the base that the Babylonians use in their math system or their number system? 60. Okay, we use a base 10, right? Everything repeats in multiples of 10. They use something that repeated in multiples of 60. Okay, but what they found out is that, okay, we've got 6 angles there at the origin that all have 60 degrees. Well, what's 60 times 6? 360. And now you might be questioning, well, what does that have to do with a circle? It has everything to do with that circle. That is a circumscribed circle around that hexagon, right? So their argument was, well, if that hexagon has 360 degrees, when I add those 6 angles up, then a circle must have the same amount of degrees. Does that make sense? Okay? Because the argument a lot of people have eventually is, okay, 360, that's awesome, but wouldn't it be so much nicer if they would have chose like 400 degrees? Because then our calculations are maybe a little bit easier with a kind of a whole round number there, right? Like obviously 360 is a whole number, but 400 may be a better one. Okay? Does that make sense to everybody? So that's kind of where the 360 has come from through history, and it's just something that's stuck. Okay, we'll use that quite a bit. Think about our time, the way we calculate time, minutes and hours and seconds and stuff like that are in base of 60, aren't they? Okay. The way we navigate and we deal with GPS coordinates and all that kind of stuff, they are provided in a lot of times in a base of 60. Okay, and I'll talk about that as we move on through the course. All right, so that's a pretty important thing to talk about. Another important thing to talk about is, and again, when we get to seeing examples throughout the PDF, I'll come back to this. But let's make a comparison to distance. If I'm going to measure the distance between here and Cleveland, how can I do that? What kind of units can I use? I can use miles, and that's what we're most familiar with, right? We all grew up in America that uses that system, right? We use miles, feet, inches, all that kind of stuff, okay? Last period, I had Irene. Irene's from Italy, right? She's more familiar with kilometers, okay? Are those numbers, when I say the distance from Lima, Ohio to Cleveland, Ohio, and I show it in miles, and then I show it in kilometers, are the numbers different? Absolutely. But are the distances the same? Yes. Okay? So we can use different units, right? You can do it in miles, you can do it in inches, you can do it in kilometers, you can do it in light years. It doesn't matter. The distances are the same, but the numerical representations for those distances are different because of the units we use. So, same thing happens in angles. Okay? You guys are familiar with measurements of angles in what unit? Degrees. Anybody know the second unit that's out there? Radian. Okay? So a radian, anybody know what a radian is or how to explain it? You probably know the conversion, right? 360 degrees is equal to 2 pi, right? Or 180 degrees is equal to 1 pi radians, right? Okay? So, and those of you that are in physics, I'm kind of talking to you. You're the people that probably have heard it. This is what a radian is, and this is true no matter what circle we talk about. Okay, no matter the size of it. Okay, you take that red distance. What's that red distance for a circle? Radius. Does radius sound a lot like radian? Okay, so that's kind of where it's coming from. We take our circle. Okay, we know our radius. We're going to pluck that radius out. So see, we're going to take this radius out here. All right. So that radius right there, that red distance, is the same as it was to create the circle, right? Okay. Let's say it's like 10 inches. Okay. I can now take that 10 inches and can I bend it so that it lays flat on my circumference or aligns itself with my circumference? Does that make sense? Okay. Still 10 inches. 10 inches walking in a straight line compared to 10 inches walking on an arc, it's still the same distance, right? It's still the same length. Now, what we create here, okay, is a lot of times we refer to this as like a subtended arc or a subtended angle. Okay, it just basically means it's an angle that's created by those two green rays. Okay, that angle right there we consider to be 1 radian. Okay, When you take out a radius and lay it along your circumference, it's tracing out the angle that we consider to be 1 radian. Is that right? And it's going to be the same no matter how big your circle is. It's going to be equivalent to, it's about 57 degrees. Somewhere in the, we'll talk about the actual value or the like decimal approximation for how many degrees 1 radian is later. But now let's look at that 1 radian. Can I cut and paste that 1 radian? Play, come on. There you go. So there's 2 radians, right? There would be a third one. Okay. Now I've got this little sliver right here, correct? Okay, that little sliver, anybody want to take a guess at what hundredths of a radian that is? 0.14. Yeah. Okay, that little sliver right there, okay, is going to be the decimal part of pi for us. Does that make sense? So when I put all 4 of those kind of sectors together, they're going to add up to pi radians. So how many degrees would that have been if I traced that out? 180 degrees, right? You make that straight angle there, so you get 180 degrees. Well, here we're seeing this show that that's actually the same as pi radians. Okay? And then if I double that, that's pi radians up there, trace it out again down here, it's 2 pi radians. Well, how many degrees is all the way around? 360. Okay, so 360 is equal to 2 pi radians. Or, obviously, if we're going to use a conversion factor, we like to use the reduced conversion factor. So we say that 180 degrees is equivalent to 1 pi radian. But that's kind of the second unit that is actually a little bit more natural. Okay, it has to do, you know, what's the circumference for a circle? What's the formula there? 2 pi r. Okay. Well, that 2 pi is our distance around, right? And our r is the radius, correct? So if our r is 1, don't we just get 2 pi? That kind of make sense? Okay. So there's links there between that idea and some of the formulas that we currently have. So what's going to happen? And this is where you're gonna fight me on it, and maybe you've fought your physics teacher on this a little bit. It's more appropriate or makes more sense to you to deal with 360 degrees because you can visualize that. You understand what that means. Okay. If I say think about 270 degrees, can you visualize how big 270 degrees would be? If I asked you to visualize 3 pi over 2 radians, can you visualize that? It's a little bit harder, right? Guess what it's the same as? 270 degrees. Okay? So I'm going to ask you to kind of start visualizing angle measurements, not in degrees anymore, but in radians. Because it makes for our algebra that we're going to use and our trigonometry processes that we use a lot more straightforward and a lot simpler to calculate, especially mental math-wise. Okay? The idea is the same as, you know, if I'm talking about and I ask you to do distances, okay, or maybe when you're first in chemistry and you're comfortable more with like ounces and grams ounces and pounds and that kind of stuff, but then they ask you to start working with grams, start working with kilograms. I would ask you to start working with distances and kilometers. You're gonna struggle with that at first. You're gonna fight against that because it's not something that you have a good idea of visualizing, right? If I ask you to talk about a velocity, you're probably going to try to represent that velocity or that speed in miles per hour, right? If I ask you to do it in miles per kilometer, you're going to fight against that. We're going to, kilometers, did I say miles per kilometer? Yeah. That makes no sense. Kilometers per hour, sorry. You're going to want to fight against doing that, but eventually the more we use it, and we have a better understanding of the conversion, the easier it is to visualize. Does that make sense? Okay. We're going to use a lot of GeoGebra because I think it's going to help you visualize some of this stuff, especially when we're talking about radians. All right. So now I want to talk about what an angle is. Okay. So an angle, what we're going to do all the time in this course is no matter what angle we're dealing with. Okay, so that, let me do it. And you guys, maybe that have a little bit of a vector background might know this. Okay, if I look at that angle right there, is its measurement the same as, let's see here, that angle right there? Is it the same as that one right there? Is it the same as that one right there? Does that make sense? I can move it anywhere I want to. And what I can also do is I can rotate. Now, I can't do that real well here in GeoGebra. Let me do this. So that angle right there is the same as that one, it's the same as that one, it's the same as that one. It's the same as that one, right? We like to look at that one because where is the vertex of that angle? 0, 0. It's at the origin, and we like that. Okay, it makes things very convenient for us. All right, so let's talk a little bit about the parts of an angle. I don't want to do it that way. Okay, so what we get is this ray right here, because it is on the positive x-axis. It's the end point of the ray is at the origin, and the ray follows the positive x-axis. So we call that our initial ray. It's our starting ray. Does that make sense? Okay. Let's see here. Let's put another point on there. What in the world? Attach. I'm not sure what's going on there. I don't know why it's putting D on that vector. That doesn't exist. Do I have something in the background? It doesn't really to. Let's just do that. Get rid of that. Get rid of that. I'm just trying to create a point here so I can trace it. There we go. Yeah. It's weird. All right, so we consider, when I look at this picture right here, right now, this is my initial ray. Because then I'm going to take and trace that ray out. Okay, so I'm going to take the purple ray, okay, and I'm going to rotate it around point A, around the vertex. And now that blue span is referred to as the angle. Does that make sense? And that's the thing that we're going to measure. The red ray, like I said, that's our initial side. The purple one, we call that our terminal side. Terminal means stops, right? Or the end. Okay, to terminate means to stop something. So we got our initial ray and our terminal ray. Okay. Now that would be considered, if we ask GeoGebra to kind of find an angle measurement here. That angle measurement right now would be 47 degrees. We can convert that to radians later on when we need to. But that is 47 degrees, and that would be the span between those two. Does that make sense? Now, it's a positive 47. And the reason I know it's positive is because we are moving when I move this angle from there to there, we are moving in a counterclockwise direction. Does that make sense? So this angle here is a positive 127 degrees. Does that make sense? Okay, now in geometry, we kind of stop at that angle there, right? We didn't talk about angles that were bigger than 180 degrees, but we can now. Okay, it just means that you keep rotating. Okay, I can have an angle at 219 degrees, and we're talking then about that blue arc. Does that make sense? Okay, that'd be the portion essentially of the circle that we have traced out. When I keep going, I can talk about 360 degrees. Okay, now GeoGebra isn't going to allow us to do this. It's not going to show the next number I want. It's going to restart at 0. But let's say that I go back up here because I still have blue. Now I'm tracing blue on top of blue, right? So I traced out 360 degrees, and then I traced out another 90 degrees. That's 450 degrees, right? We can have an angle at 450 degrees. You guys ever watch the Olympics or you watch anything like the X Games or anything like that? They talk about people doing like 360s, and they say, well, he just did a 540, or he just did a 720 or 900, right? That tells how many times they've revolved, how many times they've gone in a circle, right, on their axis, okay? That's the same thing that we've got going on here. If I want to talk about a 720-degree angle, it means that that terminating ray actually rotated around the entire circle 2 times. Is that something we can kind of visualize, understand? So that's very, very important to us. Now, if right now I've shown you I've traced out 450 degrees, let's do this. Let's not go 450. Let's go. Start over. So I'll walk out 360, and then I'll stop at 400. Okay? So that's a 400-degree angle that I've traced out, right? Well, if I just look at the angle and the rays, it's that. So if I ever am asked about a 400-degree angle, everything that is true about a 400-degree angle is exactly the same as what is true about a 40-degree angle. Does that make sense? Okay. So we like to be able to say, yeah, we're dealing with a very, very large angle, 400, but if I understand something about this 40-degree angle, that's everything I need to know about my 400-degree angle. Is that all right with everybody? Okay. And that's something that we do a lot in mathematics just across the board is being able to do that idea. If I know something about very small numbers that is exactly the same as something about something that's very large, I'd rather investigate and talk about the small one and explain it with the small one. Okay, and that's kind of what we're doing here. If we were to take our angle, and instead of moving counterclockwise, we trace out clockwise. Okay, now GeoGebra is not showing this, okay, the way I've got it set up, and that's the one issue with GeoGebra sometimes, is that the order that I set things up might not initially show what I'm trying to argue here. But there we've moved that red ray and we've gone clockwise to create the purple one, right? Well, if that's, let's say if that's 45 degrees, let's say 55 degrees. 55 degrees, okay? We would say because we went this direction, it's actually negative 55 degrees, okay? So moving counterclockwise, rotating that way, you get a positive angle. Rotating this direction, you get a negative angle. Does that make sense? Okay. Now the negative just talks about the direction of rotation. It says nothing about the fact that you have lost an angle. Does that make sense? Like I'm negative $10, I've lost $10, correct? Okay. It just talks about the angle of rotation, the direction of rotation. Okay. We'll talk about that stuff tomorrow. We already kind of introduced that a little bit. We'll come down to this. It says angles and standard position. Anybody know what time we get out of here? 36? Say it again? 34? All right, we're about out of here then. So we'll pick up here. The last class got through this. We'll pick up with this tomorrow. Just talking about standard position angles. I have assigned something on web assign. Obviously, I don't know how much of that you're going to be able to get through. Not due tomorrow.